Welcome to your next flipped lesson. This one is on all about light waves. So we had an introduction into light waves, and don't forget, light waves are unique in their own way, but do share common characteristics with other waves. All this information will go into your spiral notebook. Before you start watching this, you are going to want to make sure you have colored pencils. All right, there are some things in here that you are going to have to draw, and color is imperative, so make sure you have colored pencils. The title of this video is called Let There Be Light. Okay, to recap, light waves do not need a medium, which means they can travel through a solid, a liquid, a gas, and even empty space. How do we know this to be true? We get light waves from the sun, which allow us to see during the day. Okay, visible light is what we're talking about when we talk about light, is on the electromagnetic spectrum. Okay, it's one little chunk of that spectrum. Don't forget, the electromagnetic spectrum is organized by wavelength, long wavelength to short wavelength. Same is true for visible light. Red light waves have a long wavelength, which means the distance from crest to crest is big. Violet has short wavelengths, all right? The crest to crest distance becomes a lot smaller. And I apologize, this is a little lengthy video, so just be patient. All right, light waves can only do three things. That's it, okay? The first thing that they can do is they can reflect. All right, what this means is light waves can bounce off an object at predictable angles. All right, when you look in the mirror, you see your reflection. All right, the light waves are bouncing off of you, hitting the mirror at very predictable angles. Okay, it's very important that you know this. The angle that the light wave hits an object equals the angle it reflects off the object. And what I've drawn down here is a mirror. We have our red light wave coming into the mirror, and you can see that it is bouncing off. If the light wave hits the mirror at a 29-degree angle, which is this angle right here, it will bounce off at a 29-degree angle. All right, you have to know angle in equals the angle out. All right, very, very predictable. We're going to do some lab work this week, really focusing on being able to understand this concept. All right, the second thing that light waves can do is called refract. All right, this means that bending light. So the word refract means to bend. All right, white light, like in this classroom right now, these white bulbs that are lighting up the room, can actually bend into red, orange, yellow, green, blue, indigo, violet. Those are the colors of the rainbow. And we're going to do some lab work this week where you can use a special lens to see that white light actually can bend into the colors of the rainbow. Water is an excellent prism. All right, you've ever seen a prism where, you know, a rainbow appears somewhere because light is being bent? Pretend that this is a beaker of water and I were to put a green straw into this beaker of water. If you were to look at it from the side, it would actually look like the straw was cut in half, but it's not. The reason it does this is because water is bending or refracting, all right, the light waves hitting the straw to give it the illusion that it is actually cut in half. You're going to actually see this in the lab this week, so you'll have an opportunity to see it firsthand. All right, the last thing that light waves can do is absorb. And when you think about absorption, it's just like a sponge. All right, the light waves don't bounce off, they don't bend, they go in and don't come back out. Okay, and light waves generate heat. They have heat attached to them. All right, black absorbs all the colors of the rainbow. All right, so you ask yourself the question, why do you not wear black clothing on a hot day? If those light waves, which carry heat, hit an object and are absorbed, that heat is going to build up and generate even more heat, which is going to cause you to get hot. All right, so black is one of those colors that absorb all the colors of the rainbow, and the light waves carry heat, and so that's why you don't wear black clothing on a hot day. Now, I apologize for this next part. I'm not an artist. All right, so if we were to take a look at how the eye actually works, I have very badly drawn a cross-section of what your eyeball actually looks like, okay? This blue thing that you see here on the front of your eye is called your iris. I have brown eyes, my iris is brown. If you have blue eyes, your iris is blue, okay? The iris is what gives your eye the color. You have this very small protective outer liquid thing right here. This line is actually not supposed to go there. But it's this little thin film you see between these black lines. That is your cornea. Okay, the cornea is where light is going to enter the eye here through your pupil. Okay, it's sort of a protective shield on your eye. Okay, you have this liquid sac in the front, and this little opening between the two blue is a pupil. If a lot of light is coming into your eye, this space will actually shrink so your eyeballs don't burn. All right, if it's really dark, this space will get bigger so more light can come through to see. Everyone has a lens in their eye, and it's back here behind your iris and this sac of fluid. This lens refracts light. So the light waves come in, this piece right here actually bends the light that comes in, okay? The retina is like a movie screen, all right? The image is bent and then projected on this red piece you have right here called your retina, all right? That message then travels down here to your optic nerve, and it sends the message to your brain. And our brains pick up this stuff very, very quickly, okay? So to recap, the lens in your eye bends or refracts light waves. The image is projected onto your retina, and then the message is sent to your brain by the optic nerve. Okay, I have to wear contacts because I cannot see far distances. I'm nearsighted. What that means is when the lens is bending, it actually projects the image in front of the retina. All right, and I don't get a clear image because it's fuzzy. Okay, if you have trouble seeing close up, you are farsighted. When the image is bent through the lens, it actually gets projected behind the retina, and that's why you can't read small print and things like that if you wear glasses to read. Okay, and we're going to talk about those conditions in lab work as well. Now, something amazing that a lot of people don't really know is that our eyes actually project everything upside down. Okay, so I have my tree here, actual image. All right, the light waves from the tree are then sent to my eye. The eye bends it, which means this image up here gets put here. This part of the image up here gets put down here. So this is what my eye sees. It actually sees the tree upside down, but I have this amazing organ in my body called my brain, which at an early age, your brain is trained to flip that image right side up. So this is what we get to see. Okay, it's a pretty neat fact that, you know, as a baby, technically everything is upside down until your brain has trained itself to flip everything right side up. Now, why is it we can see different colors? All right, and that's what this last slide is about. All right, the colors of the rainbow bend at different angles. All right, so not every color of the rainbow bends at the same angle. So if we have white light coming into this prism, you can see each color of the rainbow is bent at a different angle. If they bent at the same angle, we would have white light in, white light out, okay? And so a prism's job is to separate this white light into different wavelengths, okay? So if we have this green square here, why is it green, all right? The green wavelength is being reflected, so that's the color that we see. Red, orange, yellow, blue, indigo, violet are absorbed. All right, so we can't see those particular colors. Now, are these the only colors that we have in our world? No, we can see millions of colors with our eyes. It's the combination of angles and wavelengths being reflected and absorbed, and how colors relate to each other is why we see different variations of color. You're going to do a lab this week where you can change lenses to different colors to see how, you know, turquoise is produced or magenta is produced. White, all right, why do we see white? All wavelengths of the rainbow are reflected. Why do we see black? All wavelengths of the light are being absorbed. Now, I told you we're going to be doing some lab work coming up this week, so it is important that we are following the procedures of the lab and that we are getting the most out of the lab work. These are formative, but I pull information from the formative that really go to your summative grade.